course, all the good companies tend to get defunct, they disappear.
Is it on now? Is that better? Okay. So the answer is actually historically AFRL is a research institution. It was a government research laboratory, and started really a lot of work done in original pioneering lasers, nonlinear optics, chaos, mathematical physics. So a lot of research work came out in the 80s and 90s up to 2000. But it's kind of evolved now. It's actually much less a research institute than it used to be. So just a few people and myself still try to do a little bit of base research. So I'm not here to commandeer Kazakhstan or anything like that. I'm here trying to be a scientist, actually. So that's actually what AFRL historically was, a research laboratory indeed. So the next thing is the title is Exploring Broad-Area Quantum Cascade Lasers. So as a reward for staying to the last talk, no theory. Or as a punishment, no theory. All right. So the answer is right, exploring broad-area quantum cascade lasers, because this is some experimental work I was doing this summer on QCLs. So I'm in the semiconductor group. Let me go to the next slide. So we're actually, AFRL is in several places in the U.S. It's actually headquartered in Ohio, but there's directorates all over. So we're actually in Albuquerque, New Mexico. So space vehicles is a directorate, doing a lot of space launches, and then directed energy is also in Albuquerque. So in my group is actually a semiconductor group, and there's just a few of us actually doing this. We do long wavelength diode lasers and QCLs. So I'd like to thank Frederic Griot as a colleague at Telecom Polytech. So he kind of got me into this business a little bit with some feedback. And a mutual mentor of Vasilis Maitis is Tom Gavrielides. You may know at the University of New Mexico. Well, now he's at UNM. He was at AFRL for a long time. And actually, as one other point, as Professor Anlagi mentioned, funding from AFOSR. AFOSR is actually a part of AFRL. That's the research office. And if you guys are interested, there's international organizations, parts of AFOSR. AOARD, the Asian Office of Research and Development, is based in Tokyo. And if you're interested in applying for money, you can send a proposal to them. They have a little bit of money, but they're looking at doing good science in Asia. There's also an agency in London, EOARD, trying to look for good science in Europe. So they may be of interest too. And there's actually one in South America. So it's a big compass, big things. Hopefully doing some good science. All right, so let's actually get to the talk. So let me spend a little bit of time on this, the two devices, because try to explain the difference between a QCL and a diode. Because even though I've been in the QCL business for a number of years now, it's still hard to imagine the differences between diode lasers and QCLs, because you think it's just a semiconductor laser. And everything's been done before, feedback's been done before, everything's been done before. So what am I doing anything different with the QCL that hasn't been done 20 years ago with the diode laser? So hopefully this graph will let you know, tell you some of the differences. So let's start with the acute quantum well laser that you guys all know. There's a finite quantum well that you solved as a grad student. Except this one's difficult because the effective mass in the well is different from the effective mass in the barrier, so it's not quite so simple to solve, but you can still solve it. So the transitions are an electron to hole. So what happens is carriers drift in up here, some kind of slow rate. They thermalize into the quantum well pretty fast. Now, importantly, they say if they were just sitting here and waiting to recombine, they would sit there about 5 to 10 to 15, maybe 15 nanoseconds, all right? So nanoseconds timer scale. And then they would get electron hole recombination, all right? So if you have a laser, you know, the laser cavity is only a few millimeters. The speed of light's like 3 times 10 to the 11th millimeters per second. So the photon doesn't live long in the laser. The photon lifetime is very short. So now you have a nanosecond scale of the recombination to a picosecond scale of the photon lifetime. So that ratio is about 1,000, maybe 3,000, right? So this is actually important numerically. We'll see later on. So that's the first factor. The second one is if you do, you know, if you look at the wells, you think, okay, an electron in the conduction band, it's like a parabolic band. In the holes, you get splitting, so you get a heavy hole and light hole, and these are definitely not parabolic. So when you look at the gain in here, you see there's the gain becomes a little bit of structure to the gain. And the other thing to think about these guys is there's a very strong dependence because of that. There's a strong dependence of the refractive index on the recombination. So you get electron hole recombination, and you get a local perturbation in the refractive index. So the cavity looks different, right? So the result is the stimulated emission photon looks different. So the line width broadens. And that's the origin of the line width enhancement factor, because you get the strong recombination. So, and then the line width, the intrinsic line width goes as 1 plus alpha squared. All right. And so for a quantum well, you can go anywhere from a wide band gap about 200 nanometers. The record is like 3720. They die out really fast, above 3,000 nanometers. So it is actually really easy to grow. We have MBE at our facility. We can grow on, we actually grow long wavelength stuff, anything beyond two microns. So it's only like 9 to 12 alloy layers, and you put like 3 to 5 quantum wells. And in the state of art, at like 980 nanometers, the electrical optical efficiency is like 70%. So let's jump over to QCLs. They come in really fast. See, the only way these work is you now have to apply an electric field, which is why they always show these at an angle, to show the voltage drop across that. So you apply enough electric field across it, a voltage across it, the bands suddenly align so that you can get very fast transitions. So you get a very fast transition into your upper state. Now the transition is now electron, the excited state of electron to the base state of the electron, so it's E2 to E1. So this is very fast, right? This is now it's picosecond. So now instead of nanosecond, you got picosecond. And then if you do it right, you tunnel them out with phonon-assisted tunneling, and they scatter out. So it's a fast system. Okay. So whereas before in this side with the ratio of two is like 1,000 to 3,000, now the ratio of the the lifetime to the photon lifetime is on the order of 1. So now we already changed in the theory. You've already changed a lot of things. The second thing is you have a transition from 2 parabolic bands, and so the gain function is symmetric. So the gain function is symmetric. You do Kramer's Kronade to get the susceptibility, and you're at the 0 dispersion line. So now there's no change of refractive index with the carrier difference. So in principle, the line width enhancement factor is 0. So this actually comes to play later. In fact, in reality, there's some other stuff going on, and it's about why. Right. So this is the two big differences there. The wavelength is like about 3,500 to 30 microns thereabout. So QCLs really start to fade out about 4 microns. And if you look, if you can see, this is really very difficult. So there's like one stage. So you're doing like 35 of these stages, and that's like 270 alloy layers. So it's really hard to grow. So there's not very many people that grow these actually. And in fact, in the U.S., most is grown at a foundry, IQE. And a few places in Europe do it too. But actually not very many people know how to do this correctly. And believe me, I've gotten a lot of crap before. So if anything, when people, if you're in the lab testing these, if you get something that's 10%, you're excited. So recently, a collaborator at University of Central Florida, Akadi Like, has got a 25% efficient QCL. So I think that's probably about the record efficient.
Maar daarom zie ik its efficiency as well.
Well,
The one that she claimed.
She would claim, I think, about 25 to 27 too. But, right, ordinarily I see about 7. Okay? So as for us, so while we can grow quantum well stuff in-house, we outsource our QCL. So we used to work with Northwestern University. That's one thing we like to do is try to work with different groups. That's Rezegi at Northwestern got material, but we've recently started working with Arkady Lycute. I don't know if you're familiar with the company Pranalytica. He was there for a long time. So he designs the stuff and it's grown out there, and he's a great guy to work with. So as a couple of sides, if you merge the two of these together, you get something called an interband cascade laser, which is electron hole recombination in this kind of setup. And those actually can go like 3 microns to 4.5 or 5 microns. And that's the laser that Rui Yang had built for you guys to go out. There's only, for this hybrid one, there's only Jerry Meyer at Naval Research Labs and Rui Yang, and maybe just a few other people even try to do this hybrid laser. Yeah?
I just want to mention that the interband cascade laser that Rui Yang developed, there's a version of it on the Curiosity rover on Mars, which is being used to detect methane on Mars. That's why we need it.
And we actually had money to try to do that wavelength. The wavelength is like 3.3 microns for methane detection. It's got a lot of applications. So as an aside, we were trying to do it on quantum well lasers, but they're really ratty at that wavelength. So there you go. Okay. All right, so that's the two big differences and stuff, and so they behave totally different. The other weird thing about the devices is when you get a quantum well laser, you immediately know how to bias it, because the epi side is always the anode and the substrate side is all the cathode. In a QCL, you can grow it however you want. So we used to blow up some devices because we had no idea how they were grown, because MIT would grow theirs one way, Northwestern grow the other way, and you get these things and you're like, oh, what the hell? So even turning them on in the lab can be a nightmare. Right. All right, so the next difference that's going to be important later on is a quantum well. It's gain guided, so essentially it's easy to process. You lay down a stripe of ohmic contact metal. The stripe defines your cavity. The current essentially goes straight down, and the emission comes out with minimal current spreading, and that's your stripe. You can't do that with a QCL because of all those alloy layers. You get very huge spreading of the current. So essentially what people have to do is, if you're going to do trenching, you would do this. You see there's a wet etch trench. I don't know how well you can see it, but you've actually trenched through the entire active region. All right, so two things happen is now you have a very defined rectangular cavity, and you've forced your current to flow throughout there, and the emission comes straight out. So you can't. You could do this in a quantum well laser, but you don't, because anytime you etch through the fastest thing, you create dangling bonds and it's recombination sites, and it leads to failure mechanisms. So historically, that was, figuring out how to passivate the facet was a big problem in the development of diode lasers. All right. So that actually makes the third difference between the two. All right, is the fact that you have a very well-defined cavity. So now let's take a look. So just one last change. If I looked at the diode facet, so I just made a magnifying glass and imaged a 2850 diode laser we had grown. So this is a 100 micron stripe. You kind of get this, what you would kind of guess. It's kind of this 1.5 micron wide by about 100 micron stripe, and you can kind of see this light just kind of going on. So there's transverse modes everywhere. And on top of that, it's probably like filament formation in there. Filaments related to the line width enhancement factor. The line width enhancement factor generally does nothing good, really. It causes problems in telecom lasers because it creates a dispersion penalty, which is one of the selling points of quantum dot lasers. Back when we did Z lasers, the line width enhancement factor was low, so you'd have a better telecom device. So if I just make a line scan through the intensity through it, you can see all this garbage you look at near threshold half amp and 1 amp. And that's kind of what you expect. All right, let's jump to QCL. So let's get rid of that. So in a QCL, originally, if you went a single transverse mode, say you make the stripe less than 10 microns for a 5 micron emitter, and you get what you expect, a single mode. But people said, hey, I want more power out, as I always do. So let's push the width out wider. So if you could make it wider than 10 microns, you can actually see two modes pop up. And it was kind of a nightmare for people. And actually, there's a series of papers by Capasso and other people talking about how they realized that these modes, these low-order modes, can actually phase lock through four-wave mixing and become coherent, and then you get some beam steering.
So really, this is like if you are in-gain coupled laser system.
Yes.
And do it exactly like that.
Mm-hmm. For this guy, this is their paper stuff. Oh, what did I just do? Oh, all right. Okay, so if we go to high order transverse mode, let's just look at a wide cavity and just make a simplistic assumption that you can just break it down in two plane waves cycling through a cavity back in this way. And if you did that, then we can say, okay, well, if we can make some constraints, if we have these diamond modes through here, and you can have essentially you can come up with some simple equations. And this kind of restricts the number of wavelengths you would ordinarily have in the mode numbers. So this stuff's pretty well known. All right, and then of course you have two intersecting plane waves at a facet, then you get this sine wave across the front with an odd or even solution. And then what you would think is, okay, I'm going to get all these transverse modes going. They're all incoherent, and you get all the garbage that you get. So here's what you think's going to happen. And you would get all this stuff, but in fact, you don't. So here's kind of the curious part. This is actually a 40 micron stripe. So if it was a diode laser, you would see that same kind of blur. But if I image the QCL facet, I don't see it. I see 9 modes, even though it's not uniform. This isn't even a very good one. Ordinarily, you would see ones that are very distinct modes. So, and this device turns on 1/2 amp. So what you want out of this is what we're interested in is actually in pulse power, you can get over 5 watts of power out. So one of the questions was, can you get high power and high brightness, which kind of leads to the work. All right. So in this case, there's other modes going on somewhere in here, so there's not uniformity. All right. And other people have seen the same thing too. So if you see this nice sine wave pattern, you propagate it into the far field, then you get this kind of bad ear. I call it the bad ear, the two lobe patterns. So, and then we've seen it with 100 micron stripes. There's a paper from Northwestern University looking at how they see the exact same thing with stripe widths of different ones. And you get different mode orders through here, different widths. And here's 40, but it's not always simple. You get other stuff going on. So it begs the weird question. It's like, why does it act like there's only one transverse mode going? So there's one high order mode transverse mode, but there's only one mode going. And which kind of doesn't really make total sense because there's still lots of solutions that are available. But it kind of picks out one. It turns out it picks out one, and that's what you get. So then next big question is, okay, if there's one high order mode going on, can we convert the mode into a low order mode, the fundamental mode? And so, people have done this a long time ago with fibers or diodes or trying to do stuff like that. So if you did a phase plate or another trick, you actually can, and that's something we were working on before. I don't think I can talk about it though. All right, so the question is, can we do some mode conversion? And so that's what we want to do. So this feedback experiment. Let's put it into an external cavity, look at some feedback, do some beam steering and control, and then look at the dynamics of the system. All right, so here's the only shot of theory I kind of felt obliged to put in, is the Lane-Kobayashi equations for feedback. So this is just a dimensionless equation form with the electric field and the inversion. So here's this term in red is the line with enhancement factor, so 3 to 5 or so, and a quantum well, and that's near 0 here. And there's this stiffness factor from 1,000 to 100. So everything changes, and then the feedback term is in an external cavity, you'd have a delay equation here, and of course the intensity, and then this would be a coupling efficiency of your return field. All right, so, and lots of work done this with the diodes, some work with QCLs, but if you were going to do it with a broad area, then this has to be, composed of a number of terms for the transverse modes and actually the Longstream modes. So one of the simplifying assumptions is that in a diode laser, you have one longitudinal mode and one transverse mode, and then you can do a lot of work. And then the hypothesis is that even though there's more modes going, the behavior is real similar.
Two quick questions.
Yes.
Okay, your pump, your J.
Yeah, the pump.
Roughly, what is it, 0.5, 1?
No, it's 1 to 3.
So the J is from 1 to 3?
Yeah.
And your alpha, you keep it below 2.
1.1 to 1.3. Frederic Griot would say 1.3.
Yeah.
Yes.
Okay.
Okay.
Okay, it's a nice number.
All right. Yes. Okay. So Tom Gavrilidis is going to look at this and hopefully work on that. Okay, and there's just what I said. All right, so I said, okay, so here one of the ideas. Let's put it in an external cavity, and so here's kind of the setup. Here's a laser here, the QCL 40 micron stripe. There was a couple of lenses just to collimate the lens, a polarizer if you want, a feedback mirror. So the real trick is that there's a degree of freedom to rotate the mirror as opposed to shift it back and forth. And then you can image it with the camera to get the facets, or just take it out, propagate it out, and look at a detector and just over the far away. Or actually focus in a monochromator and look at that. So just the simplistic view is you have propagating waves and you have some feedback mode coming back into it. So really, what can you do? Can you stabilize the mode or induce new modes? And of course, you really can. It's actually very easy to do. So here's a reproduction of the free running mode. And so if you do some feedback, it's very easy to do. This is just imaging the near field again. You can kind of create all these kind of weird patterns just by rotating the mirror through that. And of course, that steers the far field beam. So it's kind of nice to play with. Interesting. Yeah. Okay. I promise not there. Yeah, that's true. All right.
Why rotating a mirror change the feedback?
Yeah. Well, it's let's see. Yeah, it's kind of how you're making a kind of a complicated external cavity now. So you're introducing, now you have a field coming in, out of phase, and in timing and in orientational difference in the two. It's in the transverse direction. It's in one-dimensional rotation. Yeah. Sorry, I'm Ed. You're rotating it this way. So this angle is changing. Okay. Yeah. Though, I mean, it's not really particularly wavelength sensitive. And the change. Yeah, exactly. Yeah. All right, and you get that. And so here's some stuff. This was actually the first experiment I had done last year in Paris, just looking at the scans of across how we could we call it we just give it names just for names. Okay, so, and then in fact it actually achieved one of the things I was hoping it would achieve, is that you could essentially put all the power into a single lobe. And if you look in the far field, you've changed that 2-lobe pattern into a single lobe, and with feedback you've dropped the threshold and actually gotten a little bit more power out of it. So that was kind of cool to do. And then, actually, I don't think that's going to work on this. Let's see. Oh, yeah, it should work. Maybe not. All right. Yeah, that was just a movie of showing how you tune the laser, and then these guys, the near field, will switch around. All right, so more interesting actually is what's going on in the temporal dynamics. So, and one of the things in mid-IRs is you don't really have fast detectors like you would have in the near IR. So we're only kind of limited to like a nanosecond rise time in Mercat Telluride, at least what I have. There's clips available, but I don't have them yet that are faster. So if we take a look at the free-running QCL and look at the spectra, you can see these various peaks. And if I just hit it with a 500 nanosecond pulse, if I look at this, if I set the monochromator 0 nanometers, then I would get, this full pulse. But it's actually there's actually competition going on in these different longitudinal modes, and you can see there's this low pulse rise time. So it's not actually clean laser. If I apply feedback now, so I get some kind of the single lobe near field, and then look at fix the wavelength at 4758, then you can see these irregular pulsations, and they have this kind of pulse period to them. So this was one thing I was wondering what would happen is what the beating, the time scales are. So the time scales are on this is what 20 to 25 nanoseconds. So it's actually slow. So this beating time scale is actually slow. So it's what 40 megahertz thereabouts. And so it's kind of an interesting thing to have. It's just kind of a clue. If you just looked at another one, here's a real ratty near field look, which kind of propagates into a ratty far field. Then you can see if we look at these you can get these transverse mode competitions. You can see they're out of phase. If you use two detectors and put them 2 different points, you can see the mode oscillating, beating back. And then once again, this is really slow. It's only like 17 megahertz in this case. All right, so we're not seeing any external cavity modes. We're just seeing the feed effects. We're seeing the mode beating. Same thing. You can get this really strong beating going on in this case as the modes beat against each other if you have these two lobes. And so looking at the time scales, here we go. If the pulsation periods go down as you increase the pump parameter, the ratio. And there's on the order of 30 to 60 megahertz. Here's no clear relationship with external cavity round trip. All right, but finally, if you line the thing up, in which I think would be near straight on, then you can actually see evidence of what's like chaotic effects. So we see this, if I increase the pulsation, the pump, then you start to see these very fast oscillations. If you look at it in an FFT, you can see it's like 300 to 400 megahertz. But you have to be very careful.
Is that measured FFT or
this is measured. This is
is that a spectrum analyzer?
Yeah, it's RF spectrum analyzer, but you have to be. But here's the problem: you get the experimentals will see this right away. I've got a limited bandwidth of my detector and limited bandwidth of everything else. So I don't think I'm seeing the real oscillation frequency. I'm seeing an aliasing effect. So the frequency is probably much higher than this. In fact, the external cavity frequency should be a few gigahertz, which I can't resolve. So I think what I'm seeing here is an aliasing of even faster pulsations from the digitization of the oscilloscope stuff. Nevertheless, if we're talking to Tom and Frederic, it's kind of evidence of low frequency fluctuations in a broader QCL to route into a chaotic regime that it has. And if I zoom in, and here you can kind of see here's the digitization of one of these pulsations. So it's probably something else going on faster than that. So now I'm starting to see the external cavity oscillations that I think you would see, and then more evidence that it's going into really chaotic nonlinear regimes. So now, all right. So I can see one other thing is like in this kind of another regime of a quasi-periodic oscillation where you get some kind of beating of this 44 megahertz, which might be the transverse modes, and then, well, a measured 336 or something that's higher. So it makes a bifurcation from probably a stable state into probably a ring like that, if we pump that. So it's all dependent, essentially it comes down to dependent on the rotation angle of the mirror. All right, so it's something to discover more. So that's some of the interesting regimes. So in the broad area, you don't have to have a flat mirror. So you could say, all right, well, there was a work, we could do a self-Fourier feedback and have a lens in place. All right, so if I put it at the focal length over 2 and some kind of partial reflector, now perhaps if I feed back the fundamental mode, could I get the fundamental mode out, right? So the kind of neat thing about you could do this a broad area, but a transverse mode you couldn't do it. So there's all kinds of feedback methods you can do, and this is something I'm waiting to get some optics back with anti-reflections aren't coded. Let's try that. So if you're a solid state physics guy or a solid state laser guy, you say, oh, I see this right away. This is just a standard eye cavity. So that's the eye cavity with stability. So it should actually work. All right. So, and then finally, so what it really was trying to do is to get feedback to get a Talbot effect or a self-Fourier effect. So the question is, you could get high power with a coherent output. If you have a coupling, a global coupling in this Talbot cavity, then these devices should all actually feed back to themselves. They phase lock on a super mode, and you would get some coherent output. Or this other way, which is sub-Fourier cavity, they feed back, but the coupling coefficient is different, and you would get better discrimination of the modes, and you could get a high improved mode discrimination out. And this is something I'm trying to set up to do right now. All right. So that's actually the work. So there's really, like I said, there's really no theory. We're trying to work with Tom right now, or anybody that's kind of interested in this stuff. And so that's kind of some of the work we're trying to do there. So it's just a summary that it's easy to beam steer. It's easy to increase the brightness over a broad area. And it's kind of interesting. Really, the interesting part is how they behave so differently than the diode devices. Just the other things, just a summary of what I've had. So in the future, it would be nice to have a very fast clip or something like that to really get into and examine what's going on and doing some better control. All right, so I think that is it. So questions?
Questions for him? Yes, please.
Oh, yes.
So it's been a while since I've looked at it, but QCLs are being used at terahertz frequencies at quite long wavelengths. And I seem to remember that there was some work done on versions of those that are vertically emitting. Does that ring a bell for you at all? And or have you ever thought about how you might make one that's vertically emitting instead of?
Yeah, I haven't. I've always never liked vertically emitting. People have done these kind of vertically emitting diode stuff for a long time. I've never been a fan of it because they've never worked very well. So I'm not familiar with that work. I'm skeptical on how good it is. You essentially put a grating into it and it scatters, and it just scatters coherently. The gratings are always maybe in terahertz the spacing's big enough so you can get a high quality diffraction. At the near IR you don't, so you can get second order effects and stuff ends up going all over the place. So it never works like you think it works. But yeah, we've talked about terahertz lasers, but we have never done that. So
can you please show that quantum well structure of your laser? One of your first
slides.
slides.
Yeah, sure. Yeah, there you go.
Yeah, in here, what kind of materials are involved in each individual layer?
Oh, okay. You know, quantum well?
Yeah, I'm just
okay.
What kind of layers actually in terms of materials?
Oh, all right. Well, our stuff's at 3 microns, so we're growing a substrate of gallium timonide. So we work with aluminum, gallium, indium, arsenide, and antimony. So in the barriers, at that long a wavelength, you actually make quinary devices of all 5. So predominantly, and depending on what you want, so it's predominantly aluminum, indium, and then the arsenic and antimony, to make up for the gallium, indium, arsenide. But at QCLs, essentially, it's only a ternary, so aluminum, gallium, and arsenide.
And what's the minimal thickness of each individual layer?
Yeah, well, in a quantum well, this waveguide could be 1,500 nanometers. The quantum well itself is probably like 10 nanometers, 100 angstroms. But the waveguide is like 1.5 microns. But this is like a super lattice, so all these are maybe 30 or 40 nanometers, depending on what.
So you use MB, I guess, right?
Yes, it's MB.
And so the shortest pulse is about 500 nanoseconds?
Yeah, in this case. Okay. But that's because they're subject to heating. So I wanted to eliminate any heating effects from the experimental work.
And what would that be for the incident pulse energy, for instance? I mean, the output pulse energy.
Oh, well, let's see. You can get it's high as, like I showed, like 5 watts.
No,
peak
that's
pulse power.
Average power. But
no, that's the peak pulse power. The average power, the duty cycle is only 0.5%. So the average power is only a few milliwatts, but the peak pulse powers could be 5 watts.
Oh, I see.
Okay.
I understand. Okay.
Okay.
Tim,
Yeah.
your shortest cavity ever that you measured,
10 millimeters.
10 millimeters. The longest cavity that you ever
40 centimeters.
40 centimeters. The measurements in Paris are 40
Yeah,
centimeters.
40 centimeters.
40 centimeters.
Uh-huh.
And with these new ideas of the mirrors, you can essentially grow the mirror, right?
Yeah, right.
Kind of.
Mm-hmm.
So hybrid
Yeah,
kind
yeah.
of, integration.
Right, right.
So along the length of 40 centimeters, you
Yes.
have all these quantum well structures.
Oh, no. That's the external cavity.
This is a mirror.
I see.
The actual laser is only 3 millimeters long.
3 millimeters.
But the external cavity with the feedback can be used, well, it can be as long as you want. But 40 that's just what we had to forget with. But that actually adds a lot of external cavity modes. If you could do really short, you just have a few modes. Better feedback if you can do something like that. So.
Gentlemen, any other questions? No questions. Let's take the speaker. And the field of perception is whoever wants to join us across Are you enjoying it? You can have it. Oh, reading your papers in the past. Yeah, thank you. Absolutely, yeah. Like I looked up online, there are a lot of we would probably have to lock the room. Is that all right with you guys? Yes. Because I stole the